We have been discussing about unsigned numbers till now. Microprocessor can handle signed numbers too. So let us look into some of the instructions which are being used for 8086 and 8088 microprocessor to make our operation much simpler. So apart from these signed and unsigned numbers, we have floating point numbers too, but we cannot really directly use instructions using 8086 and 8088 microprocessor for the floating point numbers. So there is a provision that is being provided by Intel which enables you to really work on floating point numbers. It is possible using 8087 coprocessor. 8087 coprocessor has the instructions which enables you to work on either 32 bits, 64 bits, 80 bits of floating point number. Now let us go further and try to understand what we can do with respect to signed numbers. So before going to the details of signed numbers, let us understand signed numbers and how is it represented and take up the instructions that are related to the signed numbers in this particular course. An 8-bit number system can be used to create 256 combinations. That means that we have 2 to the power of 8, which is equal to 00002 0FF, that means equal to 255 in decimal. So the first 128 combination 0 to 127 represents the positive number, and the next 128 to 255 represents the negative number. So this representation of this number is provided on an 8-bit register or memory location, which we mentioned D0 to D7, which has a magnitude of D0 to D6 being exclusively for the magnitude of the number and D7 for the sign bit. Now as the sign bit is given 0, we know that it is a positive number, and when it is 1, we consider it as a negative number. So it is the user who is supposed to really understand the number to be positive or negative. The system directly considers the number as binary bits and the required operation is being done. So the implementation and the usage of this number enables us to do a much better job. So a positive number, say for example 0, we have all the 8 bits to be equal to 0. For 1, we have the least significant bit is equal to 1 and the remaining bit 0. 5, we have 0, 0, 0, 0, 1, 0, 0, 1, and when it is plus 127, the least significant bit to the 7th bit, it is 1, and the most significant bit is 0. Because the most significant bit 0 indicates that it is a positive number. Then how do you represent a larger number than 127? A word size operand is being used. Now let us look at the negative number, how it is going to be represented. So for example, it is minus 128, it is MSB is 1, all the remaining bits are 0. When it is minus 127, we have 1 followed by complete 1. So we have minus 2 to be equal to all ones, the least significant being 0, and minus 1 all being equal to 1s. So the positive numbers, we have already seen the range earlier. So how do we convert the given number to be a negative number, which we have already studied in the number system in your previous course, but to make ourselves much more convenient and recall our memory, I am just putting this particular slide to enable you to understand, saying write the magnitude of an 8-bit number without considering sign and complement the number by 1 bit and add 1 to it. This is called 2's complement representation, and 2's complement representation is being used in 8086 as well as 8088 microprocessor. Invariably all microprocessors use 2's complement number because of its advantage when we are trying to talk about the operation. When I say it becomes convenient, because whenever you perform the addition operation and subtraction operation, it is much more convenient when you are using the 2's complement than the other numbers. What are the other numbers in which you can represent the negative number? One is 1's complement number, the other one is sign and magnitude number. So sign and magnitude number and 1 complement number is not easy to handle when you are performing the arithmetic operation. Hence we always consider the 2's complement number for doing the operation. Now when you are trying to talk about a number which is greater than plus 127 or when you are trying to talk about more than minus 127, we have the range which can be really accounted for using the word size D0 to D15. See, the reason why we are mentioning D0 to D15 in this particular case is we have registers in 8086 microprocessor which we call as AX, BX, CX and DX general purpose register, as well as we have SI, DI registers. This enables us to really talk about representing the number D0 to D15, and hence we represent the negative number which is greater than 8 bits using 16-bit number, which is shown in this particular slide. We have a problem especially when we are trying to talk about the sign number operation. So, whenever there is an addition or subtraction, if the overflow flag is set, it means that the result is not correct. Now, let us take a small example and see what happens when two numbers, say for example plus 92 hexa and plus 90 hexa, are added together. So, these two numbers, when you are trying to talk about, have the most significant bit to be equal to 1, and as a result of which we cannot really consider these numbers to be the positive numbers altogether. But anyway, by considering just a number as 92 and 90 hexa, we will just see what happens when you are performing the required operation. We are trying to talk about representing this particular number in a particular way which will not enable us to give the right result because the representation itself is wrong. So, whenever we are considering the number, we will have to be very clear, trying to say that when you are representing a positive number, we need to talk about whether the number is representable. If it is not representable, definitely you cannot perform the operation that is being mentioned, because you yourself have to have the clarity. Hence, I have taken a simple point of providing 92 and 90 which are negative numbers, and you cannot say it is a positive number when you are representing the sign magnitude or 2's complement number. Now, let us take a small example and see what happens when you want to add two positive numbers, that is 72 hexa and 60 hexa. I have written a small program which you already know familiar with, trying to talk about the process of writing simple programs, but the normal termination is not given in this particular program. It is only to make you understand, stating that this is a simple program where we are initializing the data segment register and trying to access the data from the .data area into the AL register and adding the data which is in AL register with data 2. Now, look at the solution whatever you have got here. We have AL is equal to 72, which is written as 0111, and 2 is 0010. The data 2, which is in the location data 2, we have written as 0110, which represents 6, because in hexadecimal it is possible for us to represent each digit by 4 bits. And 0 is 0000. After performing the operation, the result whatever you get in AL register is 1101 and 0010. What is it you see in this particular result? You see that apart from trying to look into the result, we are also looking into the two flag register which is explicitly mentioned, that is the carry flag and the overflow flag. The carry flag is 0 because there is no carry from the most significant bit outside, but the overflow flag is set equal to 1, saying that the result whatever you have got is not right. So, the result is, when you are trying to talk about sign magnitude, we know that the MSB bit, when it is equal to 1, we say that it is a negative number, and the result is a negative number as it has an MSB bit is equal to 1. The answer we should have is not right, and we got it as D2 hexa. Now, let us analyze this particular data whatever is being given. The 2's complement of this particular number is 1101, 0010 is 0010, 1101, which is nothing but equal to minus 2D. This is not the correct answer, and why is that we are not getting the correct answer is what we need to look into. Know that the carry that is coming from D6 to D7 bit is not equal to the carry that is coming out of D7 to carry bit. So, what is it we are trying to look at? We are trying to look at a situation when there is no carry from D6 to D7 and D7 to carry being same, then obviously there is an error, and this error is being reflected by making the overflow flag set. Having just mentioned this, we now have an idea of what has to be done. Now let us look into another small example to make it much more convenient when you are talking about two negative numbers. When you are adding two negative numbers, 128 and minus 2, we are supposed to get minus some number. So that means we should have got here as minus 1 2a. See, the problem what we have in this particular case is representing minus 28 in 2's complement form and minus 2 in 2's complement form. The result what we get is 0 1 1 1 1 1 1 0. The result basically is a positive number looking into the sign magnitude number. What does it mean? It means that there is some problem with this particular in this solution also, and trying to look at in a closer way, we see that the carry that is coming from the D6 bit to D7 is 0, and from D7 to the carry flag is 1. So, the carry flag will be equal to 1, because the carry flag is not equal to the carry that is being brought from D6 to D7 is not equal. Obviously, overflow flag is equal to 1. So, this definitely proves that the result whatever we get is not correct. Now, under such circumstances, how do we avoid such type of errors when we are trying to talk about sign numbers? The best way to avoid error in sign numbers is to extend the sign number operands. Sign extension copies the sign bit D7 of a lower order byte of a register into an upper bytes of the register. In case of a 16-bit register, the sign bit is extended into another register. Now, this is what we are trying to talk about. There is an instruction that enables us to do this particular operation, saying that convert byte to word. So, D0 to D7 is an AL register, and when you say convert byte to word, D7 bit, if it is 0, D0 to D7 of AH register is all made equal to 0. If D7 is 1 and D0 to D7 is all made equal to 1, as a result of which we have a sign extension number, and it becomes convenient for us to do the operation, and the result whatever you get would definitely be correct. This instruction will copy the D7 bit, that is a sign bit, to all the bits of AH register. Let us look into a small example. Move AL is equal to 32, and we have given convert byte to word. So, before the execution of instruction, we are putting the 32 hexa as 00110010 into AL register, and we assume that the AH has got some particular value which we are not bothered about before the execution of the instruction. After the execution of the instruction CBW, we have basically the 0 that is being carried over to AH register, and all the bits of AH register is made equal to 0, as a result of which we can perform the required operation without any problem, and we will not get any error. Similarly, we have what is called convert word to double word. This is another instruction. We are trying to talk about the sign number here, because this makes us a huge difference when you are performing the signed operation. As I have already mentioned, it is the user who has to take care of this particular operation. The instruction will do its duty, and user is supposed to take up all the required operation to make sure that the error is not there. So, this particular instruction copies the D15 bit of an AX register to the DX register. This is used in signed word operands. Say for example, there is an instruction, say MOV, it is not MOC, it is MOV AX comma plus 260 hexa is the instruction. So, before execution of the instruction, the AX and AH register has got some particular value, AX and DX register has got some particular value which is written as 908F and 90 8f, some particular value, and when you give convert word to double word, and this value whatever is the instruct data what you have here as 260 is copied into AX register 0260, and 0 is in the most significant bit of the AX register, that is extended into DX register, and DX register becomes 0000. Now there is another example which would be represented as move AX comma 0F132, and before the execution there is some particular value, after the execution of the instruction. Here I have an important point to really mention. Why is that 0 is being given before F is written? It is only to say to the assembler stating that this is a number, this is not any label. See, it is only to differentiate between the alphanumeric and numeric. We need to explicitly give the assembler a particular number. So, the best option of trying to give whenever you have A to F in any number prefix with 0, so that 0F132 will enable the assembler to understand that it is a number, it is not a variable. So, variable name would have been F132 hexa can be a variable name which will not be able to differentiate. To make it understand, we put 0 and then give F123. So, F132 would really enable the convert word to double word, because the most significant bit is 1, it is carried to FFFF. Now, having said this, now we are in a position to really understand that it is possible for us to use the instructions that enables us to perform even the 8-bit number which is greater than 127 plus 127 to be considered for doing the operation. Now, here is a small example which can be really taken up. Write a program to add 2 sign numbers taking care of the overflow problem, considering the 2 sign numbers plus 90 and plus 91, both are hexa numbers, and show how the overflow can be avoided. Now, here is a small program which tries to talk about the operation. In this particular case, let me once again discuss and explain to you the process where we have dot model small dot data. In dot data we are trying to talk about data 1 and data 2 are the 2 numbers which are hexa numbers plus 91 and plus 90. The result is DW with a question mark, which says that the space has been left aside for the result to be stored in that particular place, and then the dot code starts. There is again a small mistake here which you have to note, and you need to identify this and correct it as you see such things, because move AX comma dot data will not work. We will have to write as move AX comma at data. That enables you to immediately move the address of the data segment into AX register and then move the content of AX register, which is the segment address, starting address, into data segment. Then what we have done is the next instruction subtract AH comma AH. This is only to make sure that the AH register is made equal to 0. Then the first data is being moved from the memory location whose address is being pointed by data 1 into AL register, and add the content of AL with data 2. Once this is being done, we have an instruction called jump no overflow. So, in this particular case, when you are trying to talk about 90 and 91, definitely there is an overflow condition which is being done, because we are trying to talk about AL registers which has 90 and 91 is being added to it. So, let me go to the board and explain to you what happens when you are trying to talk about this particular number. So, we have the number 1001 as 90, this is 90, 91 is 1001 0001. When you are performing the add operation, we get the value as 1000, 1 plus 1 is 01 carry, 0, again 1 plus 1 is 01 carry. We note here that there is no carry here, no carry which is coming from here, but there is a carry which has come from here to here. That means that this particular result is not correct, and we have the overflow flag set equal to 1 and carry flag set equal to 1. Now, having mentioned this, when you say jump no overflow over, it means that if there is no overflow, it is supposed to go to over and terminate the program after storing it into the result. But since there is an overflow, we have a problem here trying to say that we need to really convert all the data whatever we are now considering as the data in AL register to AX register. Similarly, the data 2, which is 91 with sign extension, and perform the operation. So, the first step what we did was data 2 is brought into AL register, convert word to double word. So, let me again represent this, what happens when you are trying to do this operation on the board, trying to say that we have sign extension, AL is being brought. So, that means that we have 1, 2, 3, 4, 5, 6, 7, 8, this is in AH register, and AL register will have the value 1, 1, 0, 0, 1, 0, 0, 0. So, this is what we have now in AX register, and this is moved into the BX register. Then after moving to the BX register, we bring the next data, that is data 1, which is nothing but 91. I think, I am sorry, this is 91 which is being brought here. So, this is 1, and now this is being moved into BX register. Now, the next data is being brought into the AX register, and the sign extension takes place, which is nothing but equal to 90. Again, it is 1, 1, 1, 1 and 1, 1, 1, 1, 1, 0, 0, 1 and 0, 0, 0, 0. Now, when we perform the 16-bit addition, the value what you get is 1, 0, 0, 0, 1 plus 1 is 0, 1 carry. So, this is 1. Then we have here, no, sorry, this one does not come here, 0, 0, 0, 1. Then we have here, this is 0, says 0, 0, 0, 0, 1 plus 1 is 0, 1 carry. So, this becomes 1, this becomes 1, 1, 1, 1, 1, 1, 1, 1 and a carry flag. We see here that the carry flag is equal to 1. Obviously, the overflow flag will be continue to be equal to 0, because the most significant bit to this, there is a carry, and from the most significant bit to carry back is 1. Since there is a carry in this particular fashion, overflow flag will be equal to 0, and the result what you get is equal to right 1. So, having mentioned this, we know now that add AX comma BX will have the right result. Now, AX is being stored into the result, and as you know, the normal termination, we have move AH comma 4C hexa and interrupt 21 hexa and end the program. Having mentioned this, now we know that how we can use the convert word to double word or convert byte to word enables us to do the particular operation. Now, let us go to the next instruction which we are interested in, especially with respect to the sign numbers. We have already learnt in the previous classes what is the divide operation. The divide operation performs 16-bit by 8-bit or 32-bit by 16-bit division possible. So, let us look at it as we go further, stating that what is this integer division or signed number division. IDivide performs a signed division of the accumulator and its extension by the source operand. See, you will have to note all the time that whenever you are performing the convert word to double word, or when you are trying to talk about byte to word conversion, it always does only between AX and AH register. When you say when you are converting word to double word, it is AX and DX register, no other register. Similarly, when you are performing the division operation also, you should always understand that the operand which you are trying to talk about is AX divided by some other register. So, the source operand may be a register or the content of the memory. So, that means the denominator what we are trying to talk about can be either an 8-bit memory or an 8-bit register. For byte integer division, the maximum positive quotient is plus 127.7f and the maximum negative quotient is 81, which is minus 128. So let us look at these 4 combinations which we are trying to talk about performing the operation, because the divisor can be 8-bit and the denominator can be again an 8-bit, either register or memory. When you perform the division operation, we have the quotient in AL register and remainder in AH register. Similarly, when you are trying to talk about 16-bit by 8-bit operation, so we are trying to talk about the numerator which is AX register and denominator can be a register or memory. So the quotient is available in AX register and remainder in DX register. When you are trying to talk about word by byte, that is 16-bit by 8-bit operation, numerator is AX register, denominator can be a register or memory, so which can be of 8 bits. So the quotient will be in AL register and remainder in DH register. Note, whenever we are trying to talk about double word, that means that we are trying to talk about DX and AX combined together, which forms 32-bit register, divided by either 16-bit register or memory, and the result would be that the quotient is available in AX register and the remainder is available in DX register. There is quite important point which you need to do after the division. If the quotient is less than FF, especially when we are trying to perform a 16-bit by 8-bit division, then CF will be is equal to 0 and overflow will be equal to 0. That means that the quotient is whatever you have got is right and the remaining is available in AH register as the remainder. If the quotient is greater than FF, that means that when you are performing a division operation and the quotient is greater than 256 decimal or FF hexa, then AH register will take part of the result. So that means that you do not get the remainder, but you get the quotient itself extended to AH register. This is indicated by the carry flag being 1 and overflow flag is equal to 1. So that means you need to really look into the flag and decide what decision has to be taken with the result whatever has been obtained. Similarly, when carry flag is equal to 1 and overflow flag is equal to 1, if DX has part of the result, but if the result is not large enough that need the DX, the sign bit is occupied by the unsigned bits and the CPU makes use of carry flag is equal to 0 and overflow flag is equal to 0. As mentioned in 16-bit by 8-bit division, we are mentioning here that even 32-bit by 16-bit division has the same operation. So having mentioned about the division operation, let us look into the multiply operation. I multiply is integer multiplication. It is also called as a sign number multiplication. We are trying to talk about byte by byte multiplication or word by word multiplication or word and byte multiplication. All the combinations of this operation is possible. So we also talk about the sign number here and you need to be careful about it because we perform the operation using I multiply and I divide for multiplication division respectively for sign numbers only. So when you are trying to talk about byte by byte, AL will have an 8-bit number and the second operand will be either in register or memory and the result is available in AX register. Similarly, when you are trying to talk about word by word multiplication, AX register will have the first operand and the operand 2 will be available in register or memory. So totally we have DX and AX combined together, which has the 32-bit results that's been available. Now it is possible to multiply 16-bit by 8-bit too. So that means that AL will have byte width saying that convert byte to word operation being done and the operand 2 would be register or memory and the result what you get is DX and AX, which will be a 32-bit register. Now having mentioned this, let us go slightly further to talk about how we can perform the required operation for using sign numbers addition and write a small program and understand how we go about. So we have here dot model small dot stack. Stack is not necessary until and unless we are trying to make use of some type of a stack operation in the instruction, but it is always preferable to use dot stack 64 to enable the system to understand that you are using some space in stack, and obviously the assembler does not give a warning when you are trying to use this particular statement as an assembler directive. Dot data, I am trying to talk about 5 data which needs to be used for addition, and we are trying to find the average of these particular numbers and then the remainder whatever you have. If you are trying to talk about the integer and then the remainder, we have the remainder which is given as dw with a question mark, which says that the space being occupied. Having defined these things in dot data model, let us go to the next part where we will be writing the code, and I will be coming back if needed to look into the data. Otherwise we will go to the next slide and try to understand how the program is going to continue. We have dot code move ax comma at data, so that means that we are initializing AX register with the data segment address and moving the content whatever is in AX register into data segment. So we initialize the data segment register. So once the data segment is registered is addressed, it will be starting point, and we can have the index register to move from that particular point to access individual data which is being mentioned in the previous slide, which is being set as dot data. Sign number as the first number is plus 13, second number will be minus 10, third memory location will be plus 19, fourth memory location is plus 14, and fifth memory location is minus 18. Average, when we are trying to talk about it, we have basically the two consecutive locations which has been assigned for the average, and next 2 locations for the remainder. Having mentioned this, let us look at how we proceed further. We initialize the CX register with 05, which is the count, the number of words that is being used. We have subtract bx comma bx to initialize the bx register with 00. Then we initialize the SI register as a pointer to point to the first location of the data in the memory by giving SIG NUM as the symbol that is being mentioned in the previous. SIG NUM is the number which is being mentioned, so which has plus 13 value. So we initialize with that particular address. So obviously it will be equal to 0000, the way in which the assembler stores it into the memory location. The first instruction is move AL comma within bracket SI. That means that it is registered in indirect addressing mode. The data from the memory location whose address is given in SI is brought into AL register. Since we are trying to talk about sign number, we don't want errors in the program, so we convert this content AL with sign extension to convert byte to word. So AH will be the AL sign extension being provided in AH register. Now since BX is already equal to 0000 hexa, we add AX and BX and store the result back into BX, so that we have the value after the addition in BX register. Then we increment the pointer to the next location. This incremented pointer will point to the next data, and then the process continues. So let me represent the whole thing on the board, the way in which I am going to debug, which you can really do it when you are trying to write a program in the lab elsewhere to make sure that you don't make a mistake. So let me go to the board and try to explain to you the process how we go about. So this, I am trying to talk about AL register content. We are trying to talk about CX register. Obviously, because sign extension is being given, I am going to use AH register also, and I will be representing everything in hexa so that it becomes convenient for us to do it. And we have BX register, which is trying to talk about the 16-bit register where the result is being stored. So to start with, let me say that the first data that is being brought into CX register is 05, BX is made equal to 0000 hexa, and AL register is loaded the first data. The first data what we have is plus 13. I am considering all the data to be hexa because it's convenient for me to really perform. So this is 13. When you are trying to talk about 13, it is nothing but 0001 0011 is 13 when you are converting it into binary. So when you say convert byte to word, so that means that AH will be equal to 00. The sign extension of this is being given here. So the next instruction is add BX comma AX, and the result is stored back into BX. So the value what we have is 0013 after performing the first operation. Then we said increment Si. So Si is one which is pointing to first location, so I will put it as equal to 0 0 0 0. Next it is being incremented to 0 0 0 1, which points to the next data. Again, when you go back to the loop BAC, loop is an instruction which decrements the Cx by 1, so this becomes made equal to 4, and Si is pointing to the next data. The next data what we have is minus 10. So I would like to take the value as minus 10. If you are trying to convert it into hexa and do that, it becomes a issue. So I will take it as equal to minus 10, and this minus 10 is nothing but equal to, say for example, 0 0 0 0 0 0 0 1. This is when you are trying to talk about 10. So minus is 2's complement, that is nothing but 1 1 1 0 1 1 1 1 plus 1. This becomes 0 0 0 0 1, and this becomes 1 1 1. So the value what we have here is F0 hexa. This is nothing but equal to F0 hexa. This MSB bit is equal to 1, so this becomes FF. I am writing this in hexadecimal. This is the number which is being given in the value with sign, and without sign the value what we have is FF0. Having mentioned this, now what is going to happen is we need to add this value to this. So we are trying to talk about the next instruction, convert byte to word, which is being extended already. Now the next one is add bx to cx. So the new value what we have is, we are trying to talk about 0013 added with FF0. So the new value whatever we have is FF0 added with 0013. This is 3. F plus 1 is 1001 carry, 1001 carry, 1001 carry. We have here the value as 0003. Now we are in a position to really understand, saying that the operation of addition is over and the value is available in bx register is equal to 03. The result is correct because the carry whatever is coming from the most significant bit to the carry is equal to last but 1 to 0, which we have already seen here. So the next operation what we have is increment, this becomes Si, which is nothing but equal to 2. Now let us look into the next loop. So when you say loop, this is decremented by 1, this becomes 3, and the process continues, and you can directly see that the result whatever you are going to get in this particular process makes it very clear to make sure that the result whatever you get would be right. And once this is being done, we have the next step, because we are trying to find out the average. We need to multiply it by 5. Sorry, we need to divide by 5. Whatever is the result whatever you got has to be divided by 5. So convert AL, put AL into 5 into AL register, convert byte to word, move AX to CX, and then BX to AX, convert word to double word. Now the result whatever you have in BX is moved into AX and it's converted to double word, because DX and AX will have the 32-bit data, and you are converting this and performing I divide. I divide enables us to perform the operation of dividing 32 bits by 16 bits, and the average whatever you have is available in AX after I divide operation. This is being stored into average location, and then the last one is DX is moved into the remainder. So the usual procedure of termination by using move AH, 4C hexa interrupt 21 is being set. End is the assembler directive which is being set to stop the program for assembling. So having just understood this particular program, we just mentioned how we are going to use I divide instruction when you are performing the required operation. We also learned how convert word to byte, byte to word, and convert word to double word has been indicated. So there are some more instructions which I would like to sum up in few minutes, because they are all very simple instructions which tries to talk about shift operation and also compare operation. So we have two shift operations. We have, one is right shift and the other one is left shift. The first one is arithmetic shift right. So arithmetic shift is used for sign numbers. Arithmetic shift right shifts the bit in the destination operand byte or word to the right by the number of bits specified in the count operand. The count operand can be 1 or CL register with respect to 8086 and 8088 microprocessor. But the higher bit processors like 286, 386, 486, you can give the count greater than 1 in the instruction itself. SAR, say for example, you say AX comma 3 is possible to give in higher processor, but 8086, 8088 takes only 1. So here is a simple instruction saying that SAR DX comma 01. So the contents of DX is 2, 3, 4, 5, and after performing the arithmetic shift, the MSB bit is retained as it is, as is being indicated in the diagram here, saying that the most significant value, if it is 0, it continues to be equal to 0, if it is 1, it continues to be equal to 1, and in this particular case, since it is equal to 0, it continues to be 1. When it is shifted to the right, the new value what you get is 11A2. I think you can really look into this particular data, write into binary equivalent and see what happens and how the process works. The assignment is left to you to do it. So that let me go to the next instruction. SAR DI comma CL is where the count can be greater than 1. So this is another instruction where I am trying to use the CL to be equal to 4. Especially whenever you want the 4-bit shift operation where you have a nibble data to be moved, we use this such a type of an instruction where CL will have 4 value. So before, for example, we have 3000 hexa and CL to be equal to 04. After the execution of SAR DI comma CL, since it's shifted to the 4 times, it becomes 0300. The reason why we get 0300 is the most significant bit of DI is 0, the same value is being retained. Arithmetic shift left or shift left is same as such because there is no change with the operation whatever is being done. But if the bit number 14 of the required register is negative and the MSB bit is 1, if this changes, obviously the overflow flag will be set. This is the only difference what you need to understand about the shift left operation. Say for example, shift SAL AH comma 01, we are trying to talk about AH register which is being shifted left. If it is equal to 32, after the execution of the instruction it becomes a 64 because it is being multiplied by 2, and this is quite obvious. Since the sign flag is not changed, it continues to have the same value, we are trying to talk about all the flags to be equal to 0. Similarly, SAL DI comma CL, where CL can have the value as equal to 4, the performance of the operation is shown in this particular side, which is quite clear and obvious. The last instruction for the day which we will be talking about is compare instruction. We are talking about the compare instruction because we are trying to talk about comparing the sign numbers. When sign numbers are being considered for comparison, obviously there are instructions which enables there are flags that are being affected. They are auxiliary flag, carry flag, overflow flag, parity flag, sign flag and 0 flag. So let us look at the way in which this particular instruction works. The destination and source both are equal to same, then we have carry flag is equal to 0, 0 flag is equal to 1 and sign flag is equal to 0. So obviously when source and destination are the same, it subtracts without storing the result and the result will be equal to 0, hence the 0 flag will be set equal to 1. Obviously there cannot be any carry flag and there cannot be any sign flag, as a result of which they are 0. If the destination is greater than source, so that means that the destination is greater than source, we say that we have the result which is positive. When the result is positive, obviously there cannot be any carry flag because subtraction of destination minus source will basically make the no carry being taken, as a result of which we have carry flag is equal to 0, the result cannot be equal to 0, so 0 flag is equal to 0, and since the signs will also not change because destination is greater and sign flag will always be equal to 0, so all the 3 will be 0. The last one which we have here is destination being less than source. Obviously, this is a situation where there is a borrow that is taking place, and hence the carry flag is equal to set equal to 1, and sign flag also changes to be equal to 1, and the result is not equal to 0. We have this to be equal to 0. Why am I trying to talk about it in this particular case, especially compare instruction, is that you have already studied this particular instruction and knew about all the three, but I am interested in trying to talk about the most important part of the jump instruction which is available for sign numbers. These are jump greater than or jump not less than or equal to. Jump no greater than and jump no not less than or equal to transfer control to the target operand by adding the displacement to the instruction pointer if the condition sign flag exclusively ORed with overflow flag or 0 flag is equal to 0. Greater than or less than or equal to is to be stated value. So, this is a way in which we are trying to talk about the sign number is also taken into the consideration when you are trying to talk about these 4 jump instruction. One is jump greater than, the other one is jump greater than or equal to, or jump not less than. Similarly, jump less than or jump not greater than or equal to. The last one is jump less than and jump not greater than instruction. So, you see all these instruction has sign flag exclusively ORed with overflow flag, or sign flag exclusively ORed with overflow flag, and then we have sign flag XORed with overflow flag, and similarly we have here sign flag exclusively ORed to overflow flag. So, that means that you need to look into sign flag and overflow flag, especially when you are considering this instruction. These 4 jump instructions are important and is used only for sign numbers, not for unsigned numbers. Having said this, let me really talk about the last one which you have here, jump equal to and jump 0. Jump equal to and jump on 0 transfers control to the target operand when the instruction pointer to the placement if 0 flag is equal to 1. So, 0 flag will maybe 1 for the sign number or for an unsigned number, hence this also could be considered for sign numbers. So, with this we complete the instructions that are being kept for sign numbers. Now, let us briefly look into 1 or 2 points. Here is a simple program, write an assembly level program to find the lowest temperature among the 10 values. Assume the data is to be like this, write a program and find out which is the lowest, make use of the sign extension and when you are comparing it, so that it is possible for you to get the right results. So, the last 2 simple example, when do you use shift instruction and rotate instruction? Now, you should know the difference between these two. Shift does not allow you to make the least significant bit come back to the most significant bit, or will not allow you to bring the least significant bit to most significant bit. Either way it is not possible, but whereas in case of the rotate instruction that is being done, that is the most important part. So, that means that no data is being lost. It can be through carry or it cannot be through carry. Having said this, the last simple question, short jump has a target of dash bytes. It is plus or minus 127 bytes. Near jump has a target of dash bytes, is plus or minus 32k. I think with this I would like to stop today's topic, and I wish you all the best. Thank you.